Hello everyone, this is Mohsen Seraj. I'm a senior application engineer Ansys working in Ozen Engineering. Today I wanna have another video about adiabatic expansion cooling process from adiabatic expansion, and the focus of this part is for phase change using CFD analysis by Ansys Fluent. Be with me. So what is adiabatic expansion? Basically, when gas passing through an opening, that the volume of the gas suddenly expands. If there is no heat transfer from the walls, so there is no exchange of heat between the system and the surrounding, then it causes the temperature drop and also pressure reducing of the gas. And this is a way of the cooling that sometimes we can use it. The benefit of adiabatic expansion is that it is very efficient regarding to the energy, because we don't need energy input to the system. The operational cost is very low, and also when it comes to the uh, using water required for the cooling, by having the adiabatic expansion cooling, we can really save uh, millions or maybe billion of the water later, which is very good for the environment too. Adiabatic expansion is not only in industry, it also happens in geology and nature, specifically when the air expands as going up, the pressure drops and also the temperature drops, so it is cold. And when we consider that, for example, for the air conditioning in the building, this is, and also for cooling system in the data centers, we can use this adiabatic cooling for adiabatic chillers and cooling towers. Basically, what we have here, that when we have flow of the warm air, that it is usually dry, when it passing through the duct with the expansion, sudden expansion, the cooling can cause even the droplets formation, water droplets formation. So we are seeing phase change in this adiabatic system. So, and the exiting air, besides that it is cooled, that it has a lower temperature, also it has increased humidity that we have. And again, the more important things is that there is no additional input here energy into the system for cooling the air and increasing the humidity of the air. So I'm going to show you that how to set up the model in Ansys and running the CFD simulation. This is the next section of this video. In Ansys Workbench, we are working on the same geometry as in the previous previous video that we have. So as you can see, the thinner part, it has a radius of 40, larger part the radius of the 200 millimeters, so 50 to 200, the ratio it is 4 to 1. And for the mesh, we use a a smaller size for the mesh, because we are working on the phase change. So no local sizing, just for the surface mesh I use a smaller size for the maximum size. The other steps are same as before, that you can see I have inlet for mass flow rate and outlet pressure, outlet and walls. This is inlet, outlet and walls. Region, I just have fluid. I consider 5 layer for the uh, boundary layer, and I created the volume meshing with the minimum orthogonality of zero point 0.2, and I improved it to 0.3. So this is, if you want to check the mesh, positive minimum volume and the minimum orthogonality, as I said, that it is 0.03, and the total number of cells is about 290,000 cells. As I said that we should see we should have much better mesh refinement because of the modeling phase change that we have. Polyhedral cells. Let's move to pheloid. Open setup for the pheloid is reading the mesh. The size, it is 200, almost 289,000 or 290,000 cells. If I check the mesh quality, as I said, it is 0.03 for the minimum orthogonality. If I want to display that, inlet outlet for the mesh, this is inlet, this is outlet, and these are the walls that you can see. This is the mesh that we have. Let's work on the setting of the model. As you can see, I consider the gravity here minus 9.8 in the negative y direction. For modeling, I consider mixture, but to define the phases, I first need to define the two phases, two materials for the liquid and vapor phases. So I just add the new material here from the pheloid library, that I can add vapor or I can add water liquid here. Copy that, you can see that. One thing is about model is that about the materials, I consider constant properties for the water liquid and ideal gas for the water vapor. And as you can see that the enthalpy is negative in both materials, for the vapor and for the liquid. Let's back to the model, multi-phase model, mixture. I use mixture, two phases. For the phases, primary phase is water vapor and secondary phase it is water liquid. For phase interaction, this is what I have for the phase interaction. Here is I can set the heat and mass transfer between the phases. So here for the mechanisms for mass transfer and heat transfer, you can see that we can have no mechanisms. So there is no phase change model, constant rate for the mass flow rate and heat transfer. We can model cavitation, evaporation, condensation here, or user defined. So we choose this evaporation, condensation, and we consider the saturation temperature of 95 degree for here in this problem. So it means that if the temperature below 90 degree, so we can have a condensation occurred, and we can have the phase change from vapor to liquid. We start from liquid to vapor, so this is the mechanism for evaporation. And if we have the mass transfer or the other way around from vapor to liquid, then we have condensation. So if we see negative mass transfer between the phases, we can see that it is a implication of the condensation. In this problem, the energy equation is also on. For the boundary conditions, for one thing that I have to be sure that in here that I consider zero operating pressure because I'm using ideal gas. So this is important to be sure about this setup. Negative G uh, in negative y direction, and then the others I just keep it by default setup. For inlet, I consider mass flow rate inlet. So I here for the gauge pressure consider about 101 101 kilopascal. For vapor, I consider mass flow rate of 1, and for liquid at the inlet I consider 0. So in this way I just have vapor coming into the domain from the inlet, and also the temperature I consider 100 degree for the vapor. For outlet, pressure outlet, again I consider ambient pressure about 100 kilopascal. Be sure to enter not this value, not 0, because the operating pressure I consider 0. This is the setup for the pressure for ideal model. 100 same as what we consider for the inlet. For the outlet also vapor, we don't have any setup. For the liquid I consider 0 backflow, so the liquid cannot come back into the domain. Walls, as you can see, for thermal conditions 0 heat flux, so these are insulated walls. So in this way it is a adiabatic system with this wall setup for the thermal conditions. Next we can go to the method. I use couple as set, and by these are all set up, only I just change it to second order upwind for the discretization of the turbulent parameters. This is important. And pressure is pressed. For monitoring or report definitions, I either here or in the solution I already talked about have to set up reports on monitoring maximum temperature or minimum temperature in the domain, and also maximum velocity in the domain. I added here one surface report, which is for vertex minimum for the static temperature at the domain. And also I wanted to check the pressure. This is one of the indications to see that if the solution converge or not at the outlet. So again, surface area weighted average for the outlet, for the static pressure at the outlet. Also, I defined a plane symmetry. As you can see, this is plane symmetry that we have, that I check the results at this plane. And let me first initialize the domain. I initialize it from inlet. Okay, that maybe make it easier for us. Initialize that 100 degree at the initial time, zero velocity everywhere, and gauge pressure of ambient pressure. Or you can use it for all zones if you want. Okay, but anyway, I started with inlet condition for the initial condition. Initialize the domain, and then you can see the vectors. I already had vectors for the velocity, pressure, and temperature at the symmetry plane. As you can see, 100 everywhere. You can see also phase volume fraction. For example, for liquid, you can see that 0. And there is another liquid contours that in the results that I will talk about it later. Let's run the simulation. You can check the cases here that we have the case. It is only about the mesh. It is something that it's some condition that we always have this to check the mesh. That, but we know that we have good orthogonality, minimum orthogonality in the domain, so we're good. Let's run it. Before that, you can save the model. Be sure that to do this before starting the simulation. Okay, let's start the calculation. These are the residuals. This is minimum temperature. This is maximum temperature. This is for monitoring maximum velocity. This is for minimum vertex minimum for the temperature. This is similar to this one. Okay, and this one for pressure at the outlet, the static pressure at the outlet. I'll back to you when the solution is done. The solution is completed. The minimum temperature in the domain is about 84. As you can see, maximum temperature is fluctuating. The velocity is also not very constant, 251 to 42. Minimum vertex for the temperature, you can see that, and also the pressure at the outlet. Let's check the contours for the temperature. So here for the temperature, as you can see, the minimum it is 84, which is below the saturation temperature of 95 degrees. So we expected to see here, besides cooling that happens in the adiabatic in the expansion system, we can have also phase change too. One other way is look at to the volume fraction of liquid. You can see that Okay, although it is very small amount, okay, but you can see that we have some changes in the volume fraction. So 0 means that, and remember it is for the liquid. So 1 is for the liquid. It is very small, but still we can see some. But another way to see the phase change is to check the mass flow rate between the phases. For this one, if I choose this, you can see that I have positive negative value. So whenever I have negative, it means that condensation happened. That here you can see that we are seeing the besides cooling, that we can find it from the temperature, phase change from vapor to liquid also happen. So this is indication of uh, condensation in the system. Let's run it for another 100 iterations, see what's happening. I'll back to you after the finishing these iterations. The solution is done after 200 iterations. Let's check some results. You can see that the minimum temperature in the domain is almost 84. We don't see many variation inside inside the domain for the minimum temperature. Maximum temperature is still fluctuating. It is not getting it, as you can see. For the velocity, you can see it is about 245 or about 245. The vertex minimum for the temperature similar to that is about 84 degrees Celsius in the domain, and pressure is getting almost constant. Let's look at the mass transfer rate. Again, high minimum values after the gas suddenly expand in the adiabatic system. I ran the model for further 200 iterations, and these are the results for 400 iterations. Mean temperature, minimum temperature in the domain around 84, and fluctuation of the uh, max temperature, you see that almost between 100 to 101 degree. So just fluctuating around 100 101 degrees Celsius for the maximum temperature. uh, Maximum velocity 240 240 245 to 250 meter per second, and vertex minimum for the temperature is also about 84. And you can see that this is for the profile or variation of the pressure at the outlet. And if we check the pressures, you can see low pressure here that we're having here right after the gas expand, much lower pressure we are seeing that. And also for the velocity, this is for the velocity, high velocity that we can see here, 247. But the main item for checking the phase change here in this example is the mass transfer rate between the phases. But the negative value shows that we have condensation. If we want to explore other material models, for example for vapor, instead of ideal gas, if we work with, say that for example, one of the real gas, and initialize the model with again inlet conditions and run the model. Minimum temperature, maximum temperature, maximum velocity, vortex minimum for the temperature, pressure at the outlet. I'll back to you when the solution is done. The solution is completed. This is the plot for minimum temperature, about 84 as before, 84 degree. This is maximum temperature, little bit less variable. Yeah, you can see that almost very close maximum and minimum for these numbers along the uh, velocity axis, temperature axis. Velocity also less fluctuated. This is also vortex minimum for temperature. And let's run it for another 100 iterations, see what's going on. I'll back to you after finishing this run. The solution is completed for 200 time step. This is for the minimum temperature, again around 84 degree Celsius. Maximum temperature around 100 degrees Celsius. Velocity 240 as before. Vortex minimum for vapor temperature, as you can see, again around 84 degrees Celsius, and this is for the profile for the pressure at the outlet. If we check the mass transfer rate, you can see that here we see negative values for the mass transfer rate. So I just want to show you that we can use different models for the material here. As you can see, we have different real gas model. It depends to the material that you are using. If you want to use the refrigerant, okay, from NIST material library implemented in Fluent, for example, for air, you can see the good things is that the range of applicability of the for the temperature and pressure is given here, so you can know that if your operating condition and what's happening after flow expands suddenly, that the temperature and pressure drops. If it is in this range, so it is acceptable that to use it. For argon, butane, you can see also for methane, I think we have it. No, not methanol, methane. These are the gas that we have. And for refrigerant, these are the list of different refrigerant that is included. If you want to work on the cooling with the refrigerant for adiabatic expansion, you can use this model to for the for the gas model, real gas nest. You have to know that the result that I showed you so far, these are all depends to the operating conditions, to the parameters for the geometry and for the materials, and also inputs for the boundary conditions. For example, I consider 1 kilogram per second for the mass inlet, but if you change it to the much smaller one, you may not see the phase change. Okay, and if you go, for example, to zero point 0.5, maybe you can see just much smaller amount of condensation at the just at the front of the opening. And also, if we have wider opening, mm, like a ratio of much more than 4 to 1, like for example 10 to 1, this is also something that you may see a different behavior for the condensation and phase change. And back here to real gas, if I want to use this real gas NIST model for refrigerant, we need also to have material properties for the vapor condition if we want to consider the refrigeration with the phase change for the evaporation or for the condensation. This is something that you have to be noted here. So hopefully by this example I can show you how to uh, set up the model and check the results for adiabatic expansion and check it the cooling and also phase change. Thank you very much for being with me.